Now let's look at the first example problem, merge intervals with quicksort. So in fact, my plan is to first talk about the quicksort algorithm, and then we'll look at this particular problem. So the high-level idea of quicksort is we pick a value that's called the pivot value from the array to be sorted. So out of all the n elements, we pick one. And then we use this pivot to partition the array into two subarrays. We want to have the property that the first subarray, the first part, all the values in there are less than or equal to pivot. And the second part, all the elements in them are greater than equal to the pivot value. So once we've done this partition step, then we just need to sort the two subarrays. If they are both sorted, then the whole array will be sorted because of the partition. So the values that are equal to pivot can go into either the first part or the second part. When it's in the first part, after the first part is sorted, they will be at the end of the first part. When it's in the second part, after all is sorted, it will be at the beginning of the second part, and then they will be connected together. Everything will be fine. So the invariance here is the element in the first part are less than equal to pivot. So this is a pseudocode for quicksort. So if we are sorting array A from position low to position high, and when low is greater than equal to high, so in fact, if we are sorting an array of one element, low will be equal to high, then we'll directly return because an array of one element is already sorted, so we don't need to do anything. So when it contains more than one element, then we first do the partition, and this partition subroutine, this partition function, will return an index. And the next part, we will sort from low to p, and then from p plus 1 to high. So where these two subarray are disjoint, and the p is the index of the last element in the first part. So that's the quicksort pseudocode. So there are several important ideas in the quicksort algorithm. The first one is recursion, because the quicksort function called the quicksort function. So this idea is called recursion, and it's a very powerful idea in computing. I often say that it seems that half of all the ideas in computing are some form of recursion. In other future CP topics, we are going to encounter recursion again and again. In mathematics, you can view mathematical induction as a form of recursion. So because to prove something holds, say, for n plus 1, we sort of need to prove that it holds for n, and then we need to prove it holds for n minus 1, and so on until we go to the base case. So that is also a form of recursion. So another algorithmic idea that's used here is divide and conquer. So a divide-conquer algorithm will divide the problem into subproblems, and then they are solved separately. And then we somehow are able to combine the solution to the subproblems into solution to the problem as a whole. And oftentimes when we do divide and conquer, sometimes we need to do the work before we divide the problem. So in fact, to decide how to divide the problem. And sometimes we need to do additional work after we solved all the subproblem. In the case of quicksort, we need to do the work to decide how to divide the problem, which is basically the partitioning part, which actually takes a linear time. So we need to partition the array into two subarray. But after we divide it, then we just need to solve each of the subproblems. When the subproblems are solved, then the problem is naturally solved. We don't need to do anything after the subproblems are solved. As we are going to see later in this topic, in merge sort, in that case, we also solve the subproblem, but then we need to do a little bit extra work after they are solved. But in that case, we don't need to do anything before we divide. The division part is straightforward in the case of merge sort. So this idea of dividing a problem into subproblem and then combining solution to subproblem together, this is called divide and conquer. So this idea is used in a few other algorithms that people generally encounter. So finally, the computational complexity. Partition will take linear time in the portion that we need to partition, because you need to scan through all the whole array, and then essentially fixing the part. If we have a big element in the beginning, when that need to be moved to the later. If we have a small element near the end, that need to be moved to the earlier part. So it's generally done by swapping those kind of elements that are auto placed, but we need to scan through the whole array. So this part takes a linear time. So then we can analyze the complexity. So assuming that the partition is balanced, then the complexity is n log n. So assuming that every time we divide the array perfectly into two parts, so then it takes a log n division step to get to each of the part to be a single element. So in the first level, the array have n elements, so partition takes time n, and then this divided into two subarrays of n over 2 each. So each of them, the partition part within them takes the time n over 2. But since there are two such partitions, the total time for partitioning at that level is also n. Then similarly, at the next level, we can view the whole array is divided into 4 different parts, and the partition is linear in the length of each of the partitions. So the combined cost is also n. So essentially, if we view this division as a level thing, then every level the cost is n, and we have at most the log n levels. Then we are done. So the complexity is n log n. But that's the case when the partition is balanced. When it's perfectly balanced, it's n log n. When it's almost balanced, it's also n log n. On average, because there are so many partitions, we can't be that unlucky so that they're all bad. So then the complexity is n log n. And there are more precise estimation of that using probabilistic analysis that we will not go into. However, there are worst cases where the complexity of quicksort will be quadratic. And this happens when the absolute worst case is every time when we partition, one of these part has a single element. Of course, there's also even worse case where if one of the partition is 0, then we're not making any progress. So, but that's something the implementation can avoid, because when that happens, the quicksort run into infinite loop. So because after partition, one of them, let's say p turns out to be equal to high, so then we will have quicksort the low high. We'll call quicksort low high, and the second part, high plus 1 high, will obviously return. It doesn't do anything because it's actually an empty array. But quicksort a low high will call quicksort with low high, which will call quicksort low high, and so on and so on. It will just keep calling itself, and the low high doesn't change, and then we'll run into infinite loop. And what happens is that this function call will exhaust the stack space which are needed for storing the variables of each of the function, and then we get a runtime error. But in implementation, we need to make sure that, for example, if we do it this way, p has to be less than high, and it has to be greater than equal to low. So p cannot be less than low, and it cannot be equal to high, because when either of that happens, we are in this degenerate case, infinite loop. But even when we avoid the infinite loop, it's possible that, say, p just equal to low, or p just equal to high minus 1. So then one of the part will have one element, the other has n minus 1. And then if we are unlucky again, then one of them has one element, the other has n minus 1. Then we will have a quadratic time. So depending on how partitioning is done, these worst cases are triggered differently. Sometimes it's triggered when the array is already fully sorted. or fully in reverse order. Sometimes triggered when the array contain all elements that are equal. So that depends on the exact way of doing partitioning. Now, how does partitioning work? And in fact, partitioning code is tricky. So I talk about this, the need to avoid infinite loop. And there are different schemes for doing it. So the one that I used in the code that we're going to discuss for solving this problem is this original horse partitioning scheme. We're going to talk about this in more detail when we review that part. But the high-level idea is we have two pointers pointing to the beginning and end, and then we just move them until we see an element that's auto-placed. When both ends point to things that are auto-placed, we just swap them. So then we keep moving the two pointer until they meet each other. So that's a high-level idea. And this Lumoto partitioning scheme is often used for teaching, but I find it a little bit less intuitive than the other. So I will not go into more detail. You can study them yourself if you want to. So in fact, when I try to implement the horse partition scheme, I actually run into bugs so in the end, I didn't spend time to fully debug it out. I look it up and then implement it. So we're going to discuss why. So basically, the code is fairly tricky. So changing anything, there's a good chance that you introduce some bug. And yeah, so I encourage you to try to implement one of the partitioning scheme yourself. So after you understand and try to duplicate it, and if you create a buggy version, then the process to understand why that is wrong will probably help you understand